In this activity, we're going to discuss linearized and differential equations. I'm going to use two examples. First, with an automobile and the momentum balance on an automobile, and the second on a heat transfer with a thermistor within a furnace. The point of non-linearizing equations is that we can take equations that may be difficult for us to deal with, and we can make them workable. There's sometimes where we just can't do things without linearizing. There's some times where we need something like a computer to do things. There's other times where it's just more complicated for our solvers and more complicated for our controllers. For control to work, we need to be able to process what current conditions are and then be able to determine what to do. And so being able to compute quickly and accurately are both important. And so sometimes linearizations are able to help us do that. Really quick, let's just 30-second overview of what linearization is. Let's think about a Taylor series. And if you were in math like me for a while, didn't really see why a Taylor series was important. But we have some function of x, and we say that that's roughly equal to, so we'll do the squiggles, it's roughly equal to f of x evaluated at x. That's what that line means, evaluated at x. And we'll do x naught, actually. Plus f prime of x naught. Actually, so it's going to be x evaluated at f x naught. So that's going to be x. This is going to be x naught. And then times, we'll say delta x. And then this would go on. It'll go on. Where we have some function where it's to the nth derivative, and then it's all divided by the nth power series. What is that called? Ooh, it's failing me. It's embarrassing. It'll come back to me. The point is if we take a linearization, one of the easiest ways to do that is just to do two terms. So we take the function value plus the derivative and multiply it. So let's think about a parabola. If we were to linearize on this point right here, we would take the slope and that value, and then the slope, and this would be our linearization. Close, it's a very good approximation. As we get further, that's not going to be good, and we need either a different linearization at different points and parameterize it, or we would need to do something else. But we have here, you can see that we have the initial point, that's f of x at x naught. We have the slope, and then how far along the slope we go will be determined by slope, that's f prime x, x evaluated at x naught, times the distance on x right here, which would be the delta x. The delta x refers to the distance along the x-axis, or whatever variable we're using, between where we linearize and where we currently are. So let's think about this in context of this momentum balance with this automobile now. So we're going to linearize a momentum balance. We're going to notice that it's going to be the gas pedal is maintained at 40%. So we have this momentum balance where we have momentum is mass times acceleration, which is the derivative of velocity with respect to time. That's equal to Fp times ut. Fp is going to be some, let's see if we can find it. Fp is a thrust parameter, so it converts ut, which is a percentage of pedal down, to the actual thrust, which is in force. So it converts our pedal percentage to a thrust, a force. Then we have minus 1/2 rho, which is the density of air, times A, which is the surface area of the car, and then CD, which is the drag coefficient, times velocity squared. So we're going to linearize this, and there's two things we need to linearize by. There's two variables at play here. There's the velocity itself, and there's also u, which is the gas pedal, which is like the input to the system. So MATLAB, we're going to discuss first how to do this symbolically, which can help, and it can also help you check your errors. I use MATLAB sometimes when there's a lot of funky math to be able to check, am I doing things right? So the momentum balances, such as some function that's a function of u and v, we'll assign alpha as the derivative of f with respect to u. And I don't see it, so that's kind of embarrassing, so we'll go ahead and type it. I'll come over here to my, there should be, I believe, the fact that we need some beta, which is equal to a function, not a function, it's going to be a frac, have two backslashes, that's why. Delta f, so derivative of f, and we'll do the denominator, which is another backslash delta with respect, the other one was u, so this one's going with respect with v. There we go. Alright, so we have two derivatives, one of the function with respect to u, one of the derivative with respect to v. You may have seen it off to the right. Let's think about this for a second though. Derivative of this function with respect to u. The first thing we want to do is we want to move this u over so we just have the function being this derivative itself. Now the derivative of this derivative, but the function is the derivative, so let's think about this. Go ahead and get out my pen. So derivative of this is going to be, that's m on the bottom all the way, so I'll go ahead and just draw that. And then with respect to u, it's itself, and so the derivative with respect to u, I'll just say du for simplicity, is going to be f p over m. And let's think through our u. When we're linearizing, instead of u, this is going to be a delta u, because we're taking the slope, and then this is the change. So we remember we have our f of x at x equals x naught plus df du evaluated at x equals x naught times delta u. So we need our delta u now. We need our df du, and then we need what our actual du is. So our derivative with respect to u at negative u. So that's going to be negative, because what that is going to be x naught, which is a constant, minus, and so that would be u naught here, for example. U naught minus u, well, our u naught is 40, derivative of that with respect to u is going to be 0. Derivative of u is going to be negative 1. So we're going to have negative 1 times this, so it's going to be negative fpm. Now let's see if I did it right. Yep. So dm du, derivative of momentum with respect to u, is fp, and it's positive, so I was wrong there. We're just taking the straight up derivative. Forget everything I said. That's from something that comes in just a bit. And then we need the derivative with respect to velocity. Well, what's the derivative with respect to velocity? This 2 is going to come out front. So it's going to be rho a cd times vt. Let's go ahead now and see how well I did. Rho a cd times v, and that's the velocity with respect to time, then all over m, and that's negative because it's negative up here. So we have our 2, and then we have our momentum balance, which is the original equation. So what we're doing in the MATLAB script is first we initialize our symbolic variables with sims. You can do sim, and then you have to say what the variable is itself and what it's stored as. Here, if we do sims, the variables are stored as themselves, which makes it a little bit easier. So momentum balance, we just put in the equation, and then for dm du, we just take this diff is doing the derivative, so the derivative of momentum balance with respect to u, and then derivative with respect to v. Now we need to linearize. We're going to substitute these in. So we've substituted in the derivatives, I should say. In our earlier linearization equation, we need the derivatives at u naught or v naught. Now what we're going to do is we're going to solve for the actual linearization. So to do that, we need to know what v steady state is. We have u steady state, and so we need to solve and figure out at that same state where we're going at some constant speed, what is v? And so let's look through the derivation here. First, if we're at steady state, the derivative of velocity is going to be equal to 0. Then we can add over to the other side, then divide over again, and then take the square root of that, and that's how we get to, let me just show the intermediate step right here. What's going to happen is we're going to have 1/2 rho, it's a rho, ACD VSS squared is equal to FPUSS. Then we take all of these and we divide them over, and then we take the square root of this, and that's how we get this function that appears right here. So then if we take the square root of this by actually just evaluating all these terms, we get 40.406 meters per second is our steady state velocity. Now we can actually evaluate it. Here we do. We evaluate v steady state is equal to the square root of those terms. And then we're able to say alpha, and we're able to set alpha and beta. Remember, alpha and beta are these derivative terms, and they're evaluated at the steady state values. So I'll go ahead and evaluated at the steady state values. We'll make this a little bit clearer. Now we're going to go ahead, similar to what we did before, we have our dm/du, which is our symbolic equation, but we're saying subs, and when we say subs, we're going to substitute something in. First is the list of what is currently within this function, and then the values we're going to substitute in for those values. For example, m, the mass, is going to be 700. The area is 5 square meters. V steady state is going to be substituted in for V. U steady state, which is 40%, is going to be going in for U. And so now we have our alpha and our beta. Now let's look at our nonlinear model. Our nonlinear model, we're going to initialize a function. We've done this a few times. This is how to do it in a one-liner where we have dv dt, the derivative of velocity with respect to time, in the nonlinear form, is equal to some anonymous function with this at symbol. That means that we're saying this dv dt now is going to be the name of it, and it's going to accept the arguments of t for time, because if we're going to integrate something, we need that as the first argument. Then we need velocity, u, and the load as arguments to the function. What it will give us back is this right here, and that's justly the equations we have right here, with this right-hand side divided by m. Now we need the linearized model. Let's look at this, and hopefully this makes sense. Our linearized model, I'm going to go ahead and we're going to write this out because this is the most important part right here. Let's just start with our initial one more time. F of x is roughly equal to f of x at, evaluated f at x0, plus f prime of x, evaluated at x equals 0, times delta x. Now, what we're going to do with this system is we're going to have some velocity balance, so dv dt is equal to some function. We're going to have two of these now. So we're going to have some function that's a function of, first, f of x at x equals 0, or x equals, the steady state values. So let's think of this actually instead of that. So let's go back. The velocity is going to be dv dt. We have two actual functions. So we'll say a function is going to be a function of f prime of u du. So at u equal 40% times delta u, and that's the delta u from that 40%, plus df, and that f is actually v, I should say, but I think f does a good job at saying what the function is. Df, this is going to be v, function of v with respect to v, evaluated at v equals vss, the steady state velocity, and that's going to be multiplied by the delta v, the difference in the velocity between the velocity and the velocity steady state condition. Both of those added together are going to give us what the change and our velocity actually is. And you can think of this when back to multivariable calculus as far as how this works, just dividing it into two different derivatives. So our nonlinear model, we're going to compare a linear and a nonlinear model. To do that, we're going to set up an array where we have lin space, which creates, it's going to go from 0 to 60 and have 61 points. So it's going to include that 0 and that 60 and give us on the dot values. Then we have zeros. That's going to be one row, 61 columns, and at after the 10th second, so we're going to set the pedal to 40. Our V nonlinear, we're going to first start out as zeros from 1 to 61, and we're going to fill in those values, but we're starting at 0. And our nonlinear, we're going to start at the same. We go ahead and clear the output so it doesn't distract you. I didn't realize I didn't do that before. So we're going to go ahead. Our load is going to be equal to 200. And so we're going to integrate this with ODE int. We've done this a number of times, so hopefully ODE int is making sense now. Let's go look at our two functions. We have dvdt nonlinear and dvdt linear. As far as integrating them, it should be pretty simple. For each step, we're going to integrate to the next step and determine the next velocity dependent on the conditions, and then go from there. Let's look at our dvdt linear and nonlinear now real quick. That's for the next portion. Same with that. dvdt linear. Oh, here we go, dvdt linear. I skipped over it. My bad. I saw this up here and thought we'd already talked about this. Point is this. We have our function. It's multiplied by alpha, that derivative that we calculated, times the delta u, which is u at some time minus 40, plus beta, which is the derivative with respect to velocity, times the delta v, which is the velocity minus the velocity at steady state. So we can do just that. Here we have some function we've determined, we've named dvdt linear. Its inputs are going to be t, v, u, and load, similar to here. Except now we have a simpler equation, which is the sum of two products. So let's go ahead. We're going to simulate this with ODE 45 and then graph this in figure 1. So you see here, we have in red the linear model and in blue the nonlinear model. You'll notice this doesn't make sense for one thing though, because at time when the pedal has not gone up, when the pedal is at 0, I should say, you see this linear model starting to rise. Now why would that be? Well, we assume that our steady state value is the condition of the pedal being at 40% and the velocity being at some 40 meters per second squared, I believe it was, or per second, not second squared. Point is, if that's the steady state condition, then with everything else constant, it will progress to start reaching that steady state condition. And so that's what's happening here. We're going to try to reach that steady state condition of 40 meters per second velocity eventually. So we're slowly progressing there, because when we say that's the steady state condition, that's what would happen if nothing else were occurring. Whereas with our nonlinear system, we have much more fidelity as we're depending on the actual conditions and the physical models. Nonetheless, as time goes on, and especially as we reach that 40 meters per second, and this heater setting, or not the heater setting, that's embarrassing. That's from the temperature control lab, and obviously someone copied and pasted this. Nonlinear, where's our plot? This is not heater setting, this is velocity, or this is pedal setting. Alright, this pedal setting is at 40, which is our steady state condition, and we're going to approach this 40, which is our other steady state condition. You can see that we're going to start being similar to the behavior of a nonlinear model. If we were to be at 40 pedal, our pedal setting we're at 40, we were at 40 meters per second, and we were to go down to 30, you'd see much similar effects because we're much closer to where we nonlinearized from. So our linearized model is going to be more accurate. Let's now discuss the thermocouple really quick. We did enough time on the theory. Hopefully this is making sense. If we're going to linearize this thermocouple, we have a thermocouple bead, which has a temperature TT, and it's surrounded by gas at TG, temperature of the gas. It also has the flame in this system, which is at the temperature TF, as a variable in the linearization. So we're simulating a cyclical gas temperature change and a step change in the flame temperature in both the linear and non-linear versions of the model. Some advanced combustion systems have a pulse mode where it kind of resonates and there's kind of this frequency that kind of happens. As a result, the temperature at any given spatial location fluctuates with time, and so we want to be able to, so we're going to represent that with a sine wave. So basically the point here is we have this temperature of the flame, which is going up and down in a sine wave. We have the gas, and we have everything else going on. How do we understand what the temperature actually is and what the temperature of the thermocouple will be? Because the thermocouple isn't actually the temperature of the gas, but if we understand the relationship between these three, we can understand what is going on because we can measure the temperature of the thermocouple. Hopefully that makes sense. The distinction is we're measuring the temperature of the thermocouple with the way the thermocouple works in electric currents, but we're more interested in the temperature of the gas and the temperature of the flame. So heat transfer is by two ways, by convection and radiation. Heat transfer by radiation is approximated by this radiation where we have the area, the emissivity, and the Stefan-Boltzmann constant. And the thermocouple bead will assume is spherical, and so we'll use that for the surface area. Here we have a few coefficients. We have the H for convection, that coefficient, the heat transfer coefficient, I should say. We also have this rho, which is the density of the air. The emissivity we talked about before, steady state temperature, and this TF, if you remember, we have to keep these things straight. TF is the temperature of the flame. TT is the temperature of the thermocouple. Oops, scrolled the wrong way. And then we have the heat capacity of the thermocouple and the diameter. So we're going to look at our function, and we're going to work on a linearized model and compare that with a non-linear model. And we'll see how they perform compared to one another. We'll go ahead, let's look at our function first. We have it down here in the bottom because it's a live script and we need our functions in the bottom. It's a little bit large to get all that stuff into one equation. So we have T, which is the things that are going to be integrated. We have temperature of the gas and temperature of the flame as input arguments as well. And we have this tilde because we don't actually need, there's no dependence explicitly on time. And so we want to, just that erases the need to have the T, and it also helps us understand that T is not actually used, but it needs to be there for spacing. So we'll take our integrated variables, and from that we'll get a temperature of the thermocouple in the first spot and linearized temperature in the second spot. We have a few parameters that we listed up above. We have those listed within our function so that our function can access them. Next we have the nonlinear Q convection and Q radiation, and from those we're able to calculate the dt, the change in temperature with respect to time for our nonlinear system. And we have T naught is equal to 1500. We'll use that here for our nonlinear version. So let's actually go ahead and go like this, make it clear what the chunks, what's what. We have the denominator, which is constant. They're all constants. But let's look at each of these terms and how we would linearize them with respect to our variables. First, let's list what our variables are in this system. We get out the pen. We have some derivative of temperature with respect to time. And that's dependent on two things. It's dependent on the temperature of the flame and the temperature of the gas. So we need to linearize this function with respect to TF and TG and then multiply it by the delta for each of them. So what is the temperature derivative with respect to, this is temperature of the thermocouple, by the way. So here we have, actually I forgot, we have three, that's why I paused for a moment. We also have temperature of the thermocouple. So temperature of the thermocouple with respect to time is dependent on three variables. So our alpha is going to be df, or so we could say dt with respect to tt. Beta is going to be dtt, that's bad tt, tg with respect to tg, the derivative. Man, this is just not my day to write. So let's go ahead, we're just going to redo it. 3 parameters. Alpha is the derivative of the thermocouple temperature with respect to the thermocouple temperature. Beta is going to be the derivative of the thermocouple temperature with respect to the derivative of, right here, beta with respect to temperature gas. And gamma is the up and down one, is the one with respect to TF. So hopefully that makes sense. Let's look at our system then. I like highlighting things. It helps me keep things straight. I have a hard enough time focusing. So let's go ahead and just, right here we have a TG. Is this highlighter even work? There we go, it's a square. There we go, TG and TT. Here we have our TF and our TT. And then our dt is equal to the sum of those two. So for our first one, go ahead and get the pen out now. Alpha is the derivative with respect to tt. We have it in 2 places. So it's going to be first negative HA plus the second one. The derivative here is going to be tt, so it's going to move a 4, and then it's going to be raised to the third. So it's going to be 4 times A epsilon sigma t to the third. Now what is this tt? Remember, we're doing the linearization here, so that's tt at, and this is all evaluated at, tt is equal to tt steady state. Lots of tt, lots of t's. So that's 1500 right here. So that's going to be, let's check right here. H times A, we have that, time minus, because these are both minuses. This right here should have been a minus, because right here it's a minus. Either way. So we have 2 minuses right here, 4 t naught to the third is what I was talking about. Times A, times epsilon, times sigma. And remember, this is all going to be divided by the new denominator because we want it only in terms of derivative of temperature with respect to time. And so we're going to take that mass times Cp right here. The mass comes from the rho, the density, and the volume, and then the heat capacity. So we're going to take those all and we're going to put them on the denominator. So let's go ahead, let's think about through our beta now, how we come up with that. Our beta is the derivative of temperature, and I'm just going to do big T this time, with respect to T gas. Now where's the gas show up? It only shows up right here. So our derivative there should be H times A, that's a big A, all over the denominator. And it is. So now we have our last one, which is our gamma. I'll just go ahead. I like the F, actually, now that I say that. It's the derivative with respect to temperature of the flame. Temperature of the flame is only used here. So it's going to be 4, it's a 4, times the area, epsilon, sigma, T flame, steady state to the third. And what do you know? That's what we have. You notice temperature of the flame, steady state is T naught as well. So our linearization, pulling it all together, is alpha times the difference, and which is the derivative at the point that we're talking about, the steady state derivative, times the distance we are from the derivative with respect to that value. Then we have beta, same thing, and gamma, same thing. So the nice thing is this is a very easy to look at, very easy to compute, very easy to see what's going on, and it decomplicates this physics-based equation somewhat. Finally, we have the 2, and then we're going to go ahead and look up here. We're going to graph them and compare our linear and nonlinear models, similar to what we did with the car. That is the car. here we have the thermocouple. So we'll go ahead, we initialize our thermocouple temperature at 1500. We create our lens space like before, and we create variables, or not variables, vectors for all of our variables. Finally, what we do is we create some sinusoidal deviation for the gas temperature so that we have that up and down pattern, kind of like what we're seeing right here with these flames. The flames go up and down because of that sonic resonation. Finally, we create the result storage arrays, and so we do a 1s times TF, and we do that bitwise TF, that way it multiplies every element by the scalar TF, or what the flame temperature would be, by the flame temperature at each moment. There we go, that's what I meant. Then we go ahead, we go through each time, we take the time slice, and we're going to integrate that time slice using ODE 45, similar to what we've done now before. Time slice, and our y0 is going to be the results of the previous time step. And then we graph it. So we'll go ahead and we'll run this section now. Because I said figure 1, our other figure is going to show up. We'll just focus on the second one. You'll notice we have our flame temperature resonating, which is good. You'll also notice that our gas temperature is slowly following that. And then with it, it's so, can we even get in there? Okay, we're just going to say view, zoom out, reset zoom. If we click on this, it may allow us to manipulate it. Except we didn't want to do this one. Apologize. Want this one. Unfortunately, let's see if we can get in there just a little bit. Our lines are so on top of each other, we can't see the nonlinear thermocouple as well, because it's following quite well. But we have the nonlinear and the linear thermocouple doing pretty well at replicating the system. Then we have the step change at half a second in. Then at half a second in, the gas temperature increases, and you can see the linear thermocouple working its way up to that line, whereas the nonlinear thermocouple follows right in line with the gas temperature, it seems. So there you have it. Thanks for sticking around. Hopefully this helped make sense of why linearization is important and how you can do it.